My research focuses on nonlinear and non-local partial differential equations, which is sort of a mouthful. But today I want to try to illustrate that these equations sort of pop up naturally in a lot of different contexts, everywhere from how autonomous vehicles interact with each other, to how particles move, to how fluid flows, to how crowds form, to how opinions are formed, how things are disseminated. In a wide variety of contexts, non-local equations come up. And recently, I've been working with a collaborator at the University of Michigan-Ann Arbor, Joe Conlon, and we work on a collection of differential equations which model fragmentation and coagulation of particle clusters. And in particular, we focus on a very specific question, and that's the long time behavior of the typical volume size of some of these models. So here's sort of a motivating example. So we've all had this, or maybe we've all had this happen just before, where we have some ice cream, we pull the ice cream out of the freezer, and what happens if you're careless and you leave the ice cream out for a long period of time? The top layer of the ice cream starts to melt. So what's happening is you have a solid in the ice cream, and it melts and it turns into a liquid. So this is an example of when particles are breaking apart, when they move from a solid state to a liquid state. And then when we put the ice cream back into the freezer, we see this crystal structure that appears. And that's when the particles are reassembling into a solid state. And our goal is to say, well, how do these liquid particles reassemble into solid particles? And how do the solid particles break apart into liquid particles? And there's a great physical theory behind this that was developed in the early part of the 20th century and then later mathematically rigorously developed in the 1960s. And the set of equations that come from these models exhibit a conservation of mass. Because what happens is when you take the ice cream out of the freezer and it melts, you still have the same amount of mass there, it's just in a different form. So the conservation of mass is an essential feature in this theory, and it sort of leads to interesting mathematical consequences. And so what we have here is a simple example of a fragmentation coagulation process. And those are the processes which we study. And so sort of abstractly what we have is you think about monomers that can coagulate into polymers and polymers that can fragment into polymers and monomers of different sizes. And so from the outset, what happens is you can imagine I have 10 balls right over here, and some physical process happens, and these 10 balls or 10 particles break up into different groups. And some can break into groups of 1 or groups of 4 or groups of 2. There's all sorts of different possible combinations that can occur. And you can sort of think, you can say, well, if I have 10 things, they can split into 1 and 9 or 2 and 8 or 1 and 1 and 8. There's a whole bunch of different combinations. And so the first thing you do in most mathematical models is you develop a simplification. And so the first order simplification are equations referred to as the Becker-During equations. And these equations say that what can happen is with these monomers and polymers, you can only break off one at a time. So only one particle can split and only one particle can join. And then what you do, and this is a common technique in mathematics, is you say, well, these particles are so small that I want to think of them as a continuous object. So I don't think of them as individual particles, counting them 1, 2, 3. I do something called I take a limit, and I basically think of this as a continuous process. So what's happening is that there's a continuum stream of these particles that are fragmenting and coagulating, and I want to figure out the equations which model these things. So I won't linger too long on the actual equations, and here they are. So what we have here is we're trying to model a density. And what I have here, I'll just sort of talk in broad strokes, is that the density of these particles of a certain volume satisfy this collection of differential equations. Now, roughly what's happening is that you have a term over here, a dc dt, that's telling you how you change in time. You have a d by dx of this thing, that's telling you how you change in space. And then you have this extra second derivative term, which is acting as a diffusion. So roughly what's happening is you're saying, here's how the density changes in time. It's being propagated by a deterministic thing. And this second order term is in some sense a random term. What it's doing is it's taking this deterministic trajectory and it's making it wobble a little bit. So in sort of an analogy what you see in finance, if you put money into a bank account, the bank account earns fixed interest, but if your portfolio is more diverse and you have a bank account, and you have bonds and you have stocks, the stocks fluctuate. So what's happening is that over time, you're following a trajectory, but this trajectory has a whole bunch of little oscillations and bumps along the way. And so what you're objected to do is you say, I would like to understand this collection of equations from a probabilistic context as well as a deterministic context. And you want to merge those two ideas. So when you're understanding these equations in conjunction with the conservation of mass, you say this is really in some sense an evolution of a collection of random events that happen. What we study in our recent work is we want to try to figure out the average volume size as time gets really large. So in the long-term time scale, what's happening to the typical volume size. When you plug the conservation of mass back into the equation, it becomes nonlinear and non-local. Now, to give you sort of a flavor of what non-local means, non-local just means that if you're in a line and someone's right behind you, someone says, go forward if you're in a line. That is an example of a local behavior. The person directly behind you says, move forward. A non-local equation would be something to the effect that says that everyone in this queue tells you what to do simultaneously. So if there's a line of 100 people, a non-local equation would say everyone in that line tells you how to move. And so that makes the dynamics more interesting and much more complicated to analyze. But you can imagine sort of analogies with things that you see all over the place, like traffic flow of autonomous vehicles. All the vehicles are communicating. So they're all the information is being fed into one vehicle from the others. The opinion formation and persuasion dynamics, how if a group of people has a particular opinion, how does that affect one individual? The same thing with crowd development, and a whole host of fluid models have this characteristic of being non-local. And so finally, what I want to mention is that, as I said before, there's a whole bunch of different equations that model these particle clusters. The one that we focus on is called the Lifshitz-Lazoff-Wagner models. And what we use is we use the physical definition of the particle coarsening. We understand it from the physical perspective. We work with the numerics, which tell us how we should expect the average volume size to grow. We think of it from the context of partial differential equations. How does the equation tell us that we're going to randomly move? And we employ tools from probability and optimal control theory to say, this is the optimal path that should be followed, and what do we expect to happen? So it's a synthesis of these ideas from probability, partial differential equations, and numerical analysis. And I want to thank everyone for your time, and hope everyone's having a great day.